Hi, Kelly. Okay, let's get started. So, quick introduction to myself. I'm Arjun. I am a freshman, and I am currently studying CS as my intended major. We'll see how well that goes after I take CS 70. But yeah, so I am an academic intern, and I am here to basically answer any questions that you guys have conceptually speaking, any from the midterms of past semesters, or any current homework or lab questions that you think are really important for your midterm two. So like I said before, when the session wasn't being recorded, I asked a lot of the students who are attending right now to send me what topics or concepts that they find most difficult. And according to most people, lists, linked lists, trees, tree recursion, that kind of stuff tends to be the most conceptually difficult. So we will be covering that mostly. There will be a few other AIs that I will switch talking with, and they will explain some questions. I will explain some things, and the session will be about 2 hours-ish long. We might even go longer than that, depending on demand. But yeah, without further ado, let's get into it. So let me begin sharing my screen. Okay, so what is the first question? I know I was asked a few questions beforehand, so let me look at those. So can you go over box diagrams with lists? Okay, so by box diagrams, you are referring to these, correct? Something where you have like, of this form? So this is a linked list. A linked list is basically a data structure that contains two values. It contains a first, which is an integer, and it contains a rest, which is another linked list. Whereas a regular list is just something that looks like this. Okay, environment diagrams with lists. Is there a particular question that you have that involves those? I would be happy to go over one. Yeah, go ahead. When looking at linked lists in terms of environment diagrams, we treat them like objects. And as most objects, we will basically create a pointer to the object, and that object will have certain variables and stuff that are part of it. And we will treat it kind of in the same way that you would treat, say, a regular list, except it's a bit more in depth given the level of complexity. Okay, I'll come back to you then. So let's go to the next question that I saw. Could we go over count partitions and that count of recursion? Okay, so count partitions. Let me quickly pull that up. So actually, participants. Okay. So count partitions. Do any of you happen to have the actual code for count partitions? In which case I can let you share your screen. Because from what I recall, the way on the study guide, Okay. So let's go to CS 61A, spring 2020, resources. Or is the study guide here? Where's the study guide located exactly? Sorry, it's a little chaotic going through to find the link because I'm using two different accounts. Midterm 2 study guide. Okay. Sorry. It's in the chat, correct? Okay. Very cool. So now we have count partitions. Okay. Thank you for typing that out. That honestly helps quite a bit. So count partitions is written definition count partitions, and it takes in two variables, an n and an m. If n is equal to 0, then we return the value 1. Else if n is less than 0, we return 0. Else if m is equal to 0, and then we will be also returning 0. And else we have a with m and minus m, m Okay, so looking at this question and the code, in essence, the way count partitions works is we have a certain number of kind of ways to divide a number such that they are a given number of partitions. So n will be our number, and m is the partitions. So looking at the code, we see several things. We see some base cases, and then we see our recursive calls. Now we know that this type of recursion is known as tree recursion. Why? Because we are taking two different routes and then doing something with the result of taking those routes and combining them to get our wanted result. So the first thing that we know right off the bat is if we're given a number, say 6. So let's say n is equal to 6. And the different ways we can partition 6 can be either 6, 0. We can do, or actually, let's do 6 with partitions 3. So how many different ways can we partition the number 6 in a way that we have 3 partitions, aka 3 numbers that add up to 6? We can do 2, 2, 2, 4, 1, 1. We can do 3, 2, 1. And we'll have some repeating cases and so on and so forth. And I'm not going to go into all of those, but essentially what we're doing is we're looking at what if we use m, so the value of m, and we subtract that from whatever our number is. So going back to our case when n was 6, let's say we want to use the number 4 as part of our partition. So what we're doing in essence is saying n minus m, and then using parts up to size m, and finding all the ways we can partition 2 with parts up to size m. And what we're doing from there is we see, oh, 2 is much smaller than m. So then as we go through each of those, we realize through these base cases that if we get to this part, because none of these will be true.
Open the fucking door.
Shloka, you are unmuted.
Oh.
Okay. So we're basically going to be taking 2 and partitioning it with things that are size up to m. So m is going to be the maximum size of our partition. And the way we want to go forward is taking 2 and finding all the ways we can partition that with m. Similar to how we started this case and we wanted to know how many ways we can partition 6 with m. One way is through using 2. And then we want to continue seeing how many ways we can use m. An excellent use of this method is actually shown through John De Niro's video. And I think he'd do a much better job of explaining how this works. So I would definitely go watch that. I can link it within the chat if you would like to see. But going on, so if we have 2 with m, that's one route. Or we could choose not to use 2. And we can see how many different ways there are of partitioning 6 without using the number 2. So remember how we had for this case, sorry, I did that in the wrong order. We can go about partitioning n, which is 6, with partitions up to size 3. Meaning we can do 1, 1, 1, 1, 1, 1, because those are up to size 3. We can do 1, 1, 1, 1, 2. We can do 1, 1, 1, 3. We can go so on and so forth. We can do 2, 2, 2, 2, 3, 1. 3, 3, so on and so forth. Yeah, I'll link it in the chat right now. Give me 1 second. I will stop sharing for 1 minute and provide you with a link. I highly recommend John De Niro's videos. Honestly, I found his explanations to be extremely helpful, and I would highly recommend it. So let me just copy the link. Okay. And there you go. Okay, back to sharing. Okay, so then we are looking at all the cases here that use the number 2. This is one way of using it. This is one way of using it. This is one way of using it. And we basically check what if we don't use the 2? Meaning, what if we do something along this or along this, along this? And if we don't use it, that's what this is for. We're basically decrementing how big our partition can be up to. And based off of how big it can be, our base cases change. Because if m is 0, there's no way to partition a number with numbers up to size 0. If the number itself is 0, the only way to partition it is by adding up 0 with nothing. It's just 0. And if n is less than 0, that means that we have exceeded the number of ways that we can partition, and that's not a valid way to partition the number. And that's what each of these base cases do. And once we have figured out how many different ways that we can partition, aka the number of ones we get in relation to the number of zeros, we add those numbers up through with m, aka the number of partitions that use the number m, or n, that use the number m, and all the partitions that don't use the number m, and then adding those up to get the total number of partitions. And mind you, when I say that we don't use m, we don't use m in one particular step. You could theoretically have 2 and then choose to use another 2, which would be using m, or you could choose to go down to 1s, in which case you would get 1, 1, 1, or like that. Or further, you could get 1, 1, 1. And these are all valid ways or routes that you can take. So I hope that makes a little more sense as to how this works. Again, for more clarity's sake, I would honestly watch John De Niro's video, because I think this is a very big concept and it will be tested. I can almost guarantee you that this was on my exam, and it'll most likely be on your exams, mainly because this is a very intricate way of testing whether you have a good knowledge of tree recursion. So my advice, watch this video, try to implement it yourself on your own. And if you understand it, then that's good. If you don't, rewatch the video. Do some more practice tests and just make sure that you really understand it. Put it on your cheat sheet if you have to, because honestly, it'll help. It'll really help. But yeah, so did that answer your question, by the way? I'm sorry, it was a little bit all over the place because I haven't really worked with Plum partitions in a while. But all right, cool. Sorry if I was unclear in any way. But so let's go on to the next question then. Okay. Let's see. What was the next question? Can you explain the difference between trees, how it relates to the linked list and the tree class? Okay, so as far as I remember, there's 2 ways that you implemented trees. There is the tree implementation and the tree class, and then there's the relationship between trees and linked lists. So let's talk about what a tree, actually, let's start with linked lists. A linked list is a data structure, meaning it's a class object that essentially has 2 variables in it. So any given link object or data structure has a
What? The girl that I gave the plant to, she had her friends there.
has a head and a tail, or you could say first and rest. The head is going to be an integer or a string, depending on what type of link you're working with. And the tail is going to be another link of any type. So in an environment diagram, a linked list will look something like this. where this is your first, this is your rest. Okay, the pointer is to the rest of the list. So this entire thing is going to be where our rest is pointing to. And then, yeah, so basically we process this through looking at each tail, and then you can either have an iterative version of going through this, or you can have a recursive version where you do something to the head, and then you will process through the rest of the list through doing link dot tail. And then you similarly you can do link dot first, link dot rest, whatever the terminology is. I'm not entirely recollecting it right now, but that's in essence what a linked list is. A tree, on the other hand, is also a data structure which has a label which is of type int or string, and branches, which is a list that contains tree objects. So typically a tree will look something like, let's do strings for now. So this is what a tree will look like. So notice how similar to how a linked list has pointers. I will simply do this and, oh, my bad. Similar to how a linked list has pointers that are pointing to the next element of the linked list, aka the rest of the list. Similarly, trees have these connections between A and B, so here, C and E, and so on and so forth. And in essence, a linked list is a one-dimensional tree, meaning there cannot be any branches within a linked list, whereas a tree can have any given number of branches. I could add like Z, I could add Y, I could add one here, M, N, so on and so forth. And unlike that, a linked list can only go up one direction, this way. You can add things to the end of a linked list in between, but you cannot have multiple things given the fact that there is only two fields, a head and a tail. Whereas a tree has a list of branches, meaning that it can have any given number and you can always append more to those branches. Meaning if you wanted to, you could add an entirely different tree as one of your branches. And that would still work. Whereas for a linked list, you cannot have dimensionality in a sense. And that is the key difference. And the way you work with them is actually very similar through recursion. But the thing with trees is that you can process them through tree recursion, since there's many different paths that you can take. And depending on what you're looking for and what you want to do with those results, you will get different kind of resulting outputs. And you want to be able to process multiple things at once and be able to combine them as a means of looking at each individual step in the tree, and then being able to bring it all back and do something with that value, whether that be returning it, creating a list of the things like the labels in the tree, and so on and so forth. And I forgot to mention, when a tree does not have any branches like this, it is referred to as a leaf. And you can check if a tree is a leaf by doing t dot is a leaf, which will return a Boolean value that says essentially, do I have branches? Do I? Yes, I do. So I'm not a leaf. If I don't, if I don't have branches, I am a leaf. If I do have branches, I am not a leaf. And that can help you as one of your base cases in many opportunities lie within finding the leaves and modifying them somehow. Does that make any sense? Or is there something that, does link dot first have to be an int or a string? Can it not be another link or a list or a Boolean, etc.? So typically you will deal with primarily ints and strings. I am not entirely sure. Let me check the implementation. Oh, sorry. Let me check the implementation of the link class for a second so that I can give you a better idea. So self.first, self.rest is equal to rest. And we assert that rest is link.empty or is in its, okay. So you don't have to necessarily be a string or an int. The reason I said typically string or int is because that's what you're going to be dealing with most of the time. By all means, you can have a kind of faux dimensionality within linked lists where you can have something like this. This is completely possible. I'm not saying it's not, but the thing is, you will most likely be dealing in like 99% of cases with something of this form rather than something of this form. Deep linked lists on your lab this week deals with link dot first being a linked list. Yeah, which is what I'm saying. It will be tested, but a majority of the questions that I've seen on tests don't really have this kind of dimensionality as a key part. Mainly because just logically speaking, it's a lot harder to process this, and they want to be able to process a lot of different topics within your test. So this might be there. Don't throw it out just yet, but I am simply saying that usually singly linked lists will be a one-dimensional quote unquote case. But yes, this is a completely valid point. Yeah. Okay. Does that make sense? Is tree the same as trees? Yeah, so sorry. This is basically just me saying it's a list of tree objects. Entire link as the first. What do you mean by that? Oh, are you referring to Pooja's question? Okay, gotcha. All right, sounds good. Wait. Okay, so we have another AI who is here. Would you like to introduce yourself?
Oh yeah, sure. Hi, my name is Aiti. I'm one of the AIs this semester for 61A2. And yeah, basically best of luck for the midterm.
Yeah. So, okay. Thank you for introducing yourself. So the next question we have is dealing with iterators and generators. Okay. So looking into iterators and generators, and also Ayati, you can feel free to answer the next question after this one, okay? Because I feel like I've answered quite a few.
Yeah, sure.
Yeah. So it's merging with iterators. Go over question 2 merge linked list as an example from lab 8. Okay, so let's go to lab 8 really quick. God, this isn't my iPad, so I am just borrowing it for today. So lab 8. Question 2. Okay, so merge. Implement merge anchor A, anchor B, which takes in 2 iterables, anchor A and anchor B, whose elements are ordered. Merge yields elements from anchor A and anchor B in sorted order, eliminating repetition. You may assume anchor A and anchor B themselves do not contain repeats, and that none of the elements of either are none. You may not assume that the iterables are finite. Either may produce an infinite stream of results. Okay, so looking at these cases, we have 2 lists of integers. We have 0, 2, 4, 6, 8, 10, so on and so forth, and then 0, 3, and so on. So we check the type of M, and we see that it is a generator. And we know by generators, it means that it is some type of function that yields values rather than returning them. And then when we list out M, we get the list, as you can see on the screen there. So essentially, what we're seeing here is we're getting an ordered list. We're getting 0, 2 from the first list, and then 3, then 4 from the first list again. 6 is common in both, meaning it's only said once. 8 from the first list, 9 from the second, 10 from the first, 12 is common to both, and then 14 from the first and 15 from the second. So essentially what is happening is the merge function is checking both lists, the first element of both, and seeing, are these the same? If they are, then we will only add it once and we will remove it from both lists. If not, if whichever one is the lesser value, we'll yield that one first and basically remove that from the list and then keep going. And so just thinking about that right away. So iter A, okay. If you don't mind, could you please put that in the chat really quick so I could just see. So it's merge that takes in anchor A and anchor B. Okay, so we have def merge anchor A, anchor B. And then it sets iter A and iter B to iter anchor A, anchor B. Okay, so we're essentially creating 2 iterators using the list that we passed in. And then next A, next B. Okay, so next A, next B is next of iter A none and next of iter B none. Okay, and then we have to write some code to basically process these. So if you remember the case that we saw, thank you for putting them in the chat, that helps quite a bit. Okay, so we have the lists 0, 2, 4, 6, 8, 10, 12, 14. So this is going to be our anchor A. And then we have our second list, which is 0, 3, 6, 9, 12, 15, which is our anchor B. And the way I think of processing this is I check the first element of both lists. And I'm going to do this in an iterative fashion. Okay. So we basically want to have it so that we go until both lists are empty, basically. So we will have some kind of while condition. Oh, my bad. We will have some while. I'm not going to specify what that is for now, but let's do the first thing. If next A, meaning if the first element that we're looking at here is equal to next B, then what we want to do is yield either one, and then not remove it from the list in this case, but we simply just want to yield it. Yeah, okay. So we yield that, and we want to make each of next A and next B update. So we do next A, next B are equal to next iter A, next iter B. Else, or if next of A is less than next of B, yield next of A, and then we want to make next of A update to whatever the next value in iter A will be. And then vice versa, we could do an elif. Technically, I think you should be able to do a regular just else, but for clarity's sake, I will be doing this. In this case, you would basically just do the same thing, except vice versa, in which case you reset next B to next of iter B. And this is what we have so far. And we want to keep this going until one of the lists are empty. Because if one of them is empty, we can basically just yield from the rest of the other one. So we can just say while actually wait. So sorry, I'm blanking on this, but the way to check if the iterator is empty is to what exactly? I'm having a blank. Ayati, do you remember?
Oh, wait, sorry.
Do you like how to check if the iterator is empty?
Okay, yeah, so for this question, you can just use like is none or is not none for next A and next B.
Okay.
In
Is
the
that
elif conditions.
yeah? So is that a dot expression, or is it just like a normal?
It's just like if next A is none.
Okay, so if is none, is that right?
I think the way that it's formatted is just like while next A is not none. And then we also want to check if so either next A or next B can't be none. So you do while next A is not none or next B is not none.
Okay, so this is basically just checking to make sure that at least one of them is not none. And while that's true, we'll basically process through. And once both of them are none, this condition will no longer be true and we can finally escape. And by then, we have basically yielded from all the values in both of the iterators within a ordered kind of like a sorted order. And that's basically how we're supposed to do it. At least I think that is the correct implementation. Any questions on how I did that? Sorry, my laptop is currently going to die. Does that make sense? Okay. That is strange. Yeah, iterator can't be empty. So I think this is like slightly faulty. I don't exactly remember what the condition was to make sure that an iterator isn't empty. Are any of you familiar with what that would be?
Yeah, so as Anita said in the chat, it will raise an error if
Yeah.
you go to the end of it. I'm pretty sure iterator have a has next implementation now.
Is there a has next for?
Oh wait, and you're saying it is
I
not
don't
next
think there's a
iterator.
has next implementation, but for most of like the questions in the midterms, you just do while true and the iterator would stop when it becomes empty.
Yeah.
Yeah. And for this question specifically, I think after this in the else conditions, you also might want to like check if next B or next A is none or not none. Or or outside the while loop, you can yield like the very last elements.
Because what I'm thinking the issue with this, because the next takes in two values for this question. Oh, yeah, you might have to do next comma none. It's because the next iterative B is the value returned and the error is raised. Oh, is that new?
Yeah, I think this is new for this semester. I think they have to do next iter B comma none or next iter A comma none.
Okay, I see. Yeah, so in that case, it'll basically just point out none when there's like an error, meaning it's empty. So in that case, sorry, I'm not entirely familiar with this because we didn't have this implementation, but you would basically just, wherever I have next, you just do with none. And similarly for here and here, you'd want to do the same thing. It's just in this lab. Interesting, okay. Yeah, no one really asked me about this question today, so I was not aware, but thank you for pointing it out. Does that make sense, or is it still not working in the code? Still erroring. Huh. Oh, okay. Thank you for coming though. That's strange.
What's the error? Like, what is your output?
The person who asked had to leave, so
Oh, okay.
I'm not sure. Kareem, Ayati, do you have any idea of what could be the issue?
Yes, I was doing this in lab yesterday, and so if you have this like exact code after the while loop, you would also want to. I think like the error that I was seeing was that the last element of both the last element wasn't being yielded, like the very last element. So after your while loop, yeah, exactly what Jeremy's saying. So at the very ending, you're going to end up with one iterable, which is none, and one which has an int. So after the while loop, you want to check like if next A is none, then you yield B. If next B is none, you want to yield A. That should fix the error. It's what the people did in lab yesterday, but you can just double check.
I guess you could also just do yield from, I guess, yield from iter A and then yield from iter B, just in case. Because if either of these are none, then they will simply just return nothing. And then it'll make sure that both the lists are completely emptied out. Yeah, I think this should work.
I don't know. I'm wary about the yield from iter A and yield from iter B part. I'm not entirely sure how that works in generators. Because is it doing it incrementally? It's yielding. Because if you're given an infinite sequence there, you might get an error. But
Yield from yields incrementally. So every time you do next, it
Oh, yeah.
should
Then, yeah.
yield one at a time.
Okay.
If you did like a list of this generator, then only would you get multiple values at the same time. But this should give you one at a time. Okay. Well, I will be passing on the next question to Ayati. Here, I'll stop sharing my screen and I will let her answer. Ayati, you can go ahead.
Yeah, sure. And which question is it?
This should just be in the chat. The
Okay.
next question that I saw, let me just quickly double check. The next question is, could we go over how we can figure out the order of growth of a function?
Can you see my screen?
Yeah, we can see it.
Okay, yeah. So order of growth. Yeah, sure. Okay, so I actually went over. There's like a cheat sheet. So okay, it's just like an introduction to what order of growth is. Order of growth, you're basically just characterizing how much of time like a function takes to run. So what you're basically seeing is you're calculating the amount of resources needed to run the function, and you're trying to model how the runtime of the function, like how it behaves as the input keeps on getting like larger. So there's for 61A, there's only like a few ones that you need to know. One is constant runtime, which is modeled by theta 1, linear, modeled by theta n, quadratic, n squared. Yeah, I'll just write these down. To write these down. Okay, so it's most of the examples in your midterms are 2 raised to power n, but like in general, it's b raised to power n. But the most common ones that show up in the 61A midterms are 2 raised to power n or like n squared right here. And then the last one is logarithmic. So theta log. So what exactly does this mean? So say we take linear, for example, that means that linear, it means that when you increase the input by say like n, then the runtime is also going to increase by that amount. So just for an example, like say you have a function for I in range n, and then say we're just like printing midterm, and Yeah, okay. So say n is 2. The amount of work that's done by this function is 2, right? Because it's printing this twice. But say n increases to 100, then the amount of work done is 100. So as long as you keep on like increasing the input size, the amount of time that it takes a function to run it also increases linearly. So we would say that this function has a runtime of theta n. And if this isn't making any sense, you can stop me at any point. I can just go over like a few examples of the other runtimes. Is that all good? Okay, perfect. So I'll just move ahead. So this is for linear. Yeah, so mostly like if you see a single for loop, that's generally going to be a linear runtime. Another thing, like for example, I think this was in the 2019 final or something where they were inserting, it was called like insert front link and val. And I don't remember like the exact function, but what this was doing is that it was giving you a linked list and a value, say like 5, and this is a linked list. And then you had to insert, the function was inserting the value at the very beginning of the linked list. So like 5 would be inserted at the beginning of the linked list over here. So, and then one of the questions was model the runtime of this. And the answer for that would be, so this is actually, it would be theta 1 constant runtime. And that's because no matter how long the length of this linked list is, you're still only inserting a value at the very beginning. So like the amount of work that you're doing is constant. And yeah, this is a little tricky, but just like how you want to approach these problems is you want to take a small sized input, see how much work the function does, and then increase that, keep on increasing that, and try to model the pattern by which it's changing. So over here, even if the length of the linked list is like 2, you're still only doing one amount of work, which is you're inserting it at the very beginning. Even if the length of the linked list increases to 100, you're still doing one amount of work. The next question after this was like insert back, which is similarly, they give you a linked list and then another value, but this time instead of inserting at the front, you had to insert it at the back. And yeah, if you can, yeah, so the runtime for this is actually theta n, and I hope it kind of makes sense why, because this time you're inserting at the back, which means you would need to iterate through the entire linked list and then add it at the back. So say the linked list had length 4, then you iterate through 4 elements and then you add val at the ending, right? But if your linked list length increases to like 400, then you have to iterate through 400. You have to iterate through the linked list 400 times to reach at the very ending, and then you add val. So the amount of work that's done when it's 400 is actually 400, and when it's 4, it's 4, because there's a while loop. Or so a singular while loop system is generally like linear. You can just note that down. Generally like single loop. Constant. Another example of constant would be like lambda x returns x. That's constant again. Yeah, and then for most of, just some more examples, quadratic means that as your input increases, the runtime increases by like a quadratic factor. So typical examples are like double for loops. So yeah, so say you have like for I in range, whatever n, for j in range n, and then again, so you're just printing something. So the amount of work done in total over here is n into n, because you go through this entire thing n times. And for each of that, you're going through this n times as well. So that's n squared. If say these were like different lengths, you were going for I in range n, and then you were doing for j in range m, then the runtime here would be theta n into m. So yeah, this is also one of the examples from one of your past papers, I think. Yeah, and then coming to exponential. Exponential is kind of the tricky one, but this is generally for most tree recursion problems. For most tree recursion problems, you would have like an exponential one time. So like a simple example would be the Fibonacci function. So say you had a like def fib n, and then when I'm missing something, returns n. Otherwise, you call. Yeah, so this is like the general structure of a Fibonacci function, and the runtime for this, how you can calculate it is, okay, so for most tree recursion problems, you would have gone over like the branching structure, which is to model like the number of calls made. So yeah, we'll do something similar. So say when n is 2, it calls fib on 1 and then on 0. But like if the input was 4, it keeps on branching out. And for each one, there's 2 calls made for each input. So yeah. And we'll just this keeps on continuing. So essentially, if you keep on increasing n, the number of calls, like the number of work that's done, is 2 raised to power n, because there's two branches made at every single level. So the runtime for this is theta 2 of n. So most tree recursion problems, because we're only calling the other function twice, we're calling like the function itself twice, the runtime for it is generally 2 raised to power n. So if there's a tree recursion problem, like your best bet is like 2 raised to power n. Yeah, and then lastly, logarithmic. This is kind of the rarest one, but this is where, like, say if there's any input being divided. So say there was something involving like n by 2. So that means like, so if you model that, then the number of times a function is run would be log n base 2. Yeah, so this one doesn't really show up that much. The main ones that you have to worry about is linear, quadratic. Yeah, basically the runtime questions are more than like a mark on the midterm, so you don't need to worry about them too much. But yeah, just let me know if you have any questions on this. Okay. Yeah, do you have any other questions on runtime? Okay, if not, we can like move to the next question. Yeah, if anybody has any other questions, you can put them in the chat. Or you can like message Arjun or me. Yeah, the only thing you only need to know the type of route. So pretty much all that you would only need to answer. Most of the questions given on the midterms is just like a multiple choice question, and they'll give you multiple options like theta n square, theta 1, and you just need to pick one of them. So yeah, you honestly don't need to know this much, this like way too much in depth. Yeah, you won't do that in section 1B. Add deals. Okay. Add deals. Which question was that? Oh, okay. On lab 8? Okay, yeah, sure. So yeah, okay, so add leaves. It takes add d leaves one. Add d leaves. Yeah, so for this one, okay, I think I'm not gonna go too much in depth on what the function is asking. I think you would have gone over that in lab, but yeah, they've given a hint, which is to use a helper function to keep track of the depth of the node, because you need to add the value of v depth times to every node. So we can just define like a helper function. I'm just gonna call this add leads, and we want to keep track of the depth, right? And you know that the value doesn't change, so you actually don't need to keep track of the value, but I know some people who did that, and that'll still work, but the only thing we need to keep track of is the tree and the depth. So we have this. Okay, yeah, and how I like to start doing like helper functions is I'll just make the call over here. So when this function starts, you want to call it on the tree, and then it's at a depth of 0. So this is your first call. Yeah, and now we can start working on the helper function itself. So Yeah, let's just think of the recursive call first. So like most of the other tree questions, you know that you have to call this function on every branch in the tree. So we can just start with for b in t dot branches. Yeah, this is question 4 on the midterm lab, by the way. Yes. For b and t dot branches. And then you know that we want to make the recursive call on each branch, right? So that's how we update like the first parameter. The next thing that you want to do is, obviously we're keeping track of the depth. And you know that every time you make a call or every time you like go into another branch in the tree, the depth is going to increase by 1. So we would increase d by 1 over here. So this is like your recursive call. And then now you're done with that. Okay, so basically while writing this, like I take the recursive leap of faith and I assume that whatever that the function is somehow extending like the branch with the leaves. So that's how you write the recursive call. And now let's think about like doing the actual work. So what exactly are we trying to do? So we have like, if there's a tree, 3, and then they're asking with the value 5 to like extend it. Say this is a leaf. We've reached a leaf and there's like a tree on top of this. I'm not going to draw it out, and the depth over here, this one is 3. So that means that we want to add 3 more leaves. So what exactly is happening? So over here, there's like, 3 was initially a leaf, right? And 3 was initially a leaf, and now we're adding in more leaves. So we're extending the branches. So at the beginning, like the branches of this leaf are null. It's basically nothing. So we're just like creating branches over here. And for other points in the tree, when you want to extend it, you're basically like adding a new value into the branch. Sorry, my diagrams aren't the best, but yeah. So what we're trying to do is you're like trying to extend the branches, right? So branches are lists. So there's a lot of different ways you can add elements to a list. So the one over here that we can use is extend. And I'm going to be using extend instead of append, because append, you just use it for adding one single element. For this, we have to account for like multiple inputs. So that would be like t dot branches. And now we're extending the branches list. Remember that this is a list. So yeah, t dot branches dot extend tree v. Right, so we're supposed to add in leaves with the value v. So this does that. But remember that we want this to be added in depth times. So we're just going to do, for depth times, we can basically just like run it through a loop for range d. Yeah, and this is basically your entire question 4. Do you have any questions on like how this happened? I think this was like Annalise. Are you okay with that? Should I explain it again? Okay, yeah, good. Okay, so we can move on to the next question then. Hello, do you have any tips on navigating skeleton code that doesn't seem intuitive to whatever approach you may have in mind? Yeah, okay, yeah, so this happened with me a lot for most of the midterms. So what you can just do is like, don't follow, just write out your own skeleton like on the side of the page, and then try to see how you can manipulate that to fit into their code. Yeah, they do have like a really restrictive approach sometimes, but most of their helper variables will have like, there'll be hints in their names, so you can use that to like alter in your written code and then fit it into theirs. Let me just see, you're asking a fall 2017 midterm 2 question 4. I'll just pull that up. Just give me a minute.
Just a side point while she's pulling it up. When I deal with skeleton code, I typically look at it two different ways. If I know one way of how I would implement it, I ignore the skeleton for a little bit. If I don't know what I'm doing and I look at the question, I will use the skeleton to guide my thinking. Like I already said, look at the names of the variables. Typically, they will give you hints as to what type of things that you are trying to keep track of and or kind of measure. And based off of that, you are able to proceed further with your, code writing. And yeah, that's basically just my 2 cents.
Michelle, are you talking about question 4 part A or question 4 part C? Part A, okay. Yeah, if anybody else has any other questions in the meantime, you can ask. Arjun can probably answer them.
Yeah.
Would append make a difference? Yeah, Arjun can take that.
Yeah, so the way append works, right? So append takes in values and basically creates a list, or not creates a list, it actually just adds those values as entries into your existing list. Whereas extend will basically take a list that you put into it and merge it with another list. Like it'll combine the two. So append takes in values, essentially plugs them into part of the existing list, whereas extend takes in two separate lists and combines them together, hence extending the existing list. I know it's a bit unintuitive to think about at first, but just think about what each takes in. Append takes in strictly values, whereas extend will take in a list and make it part of the list that you're extending from. So if you put in a list into append, it'll actually have kind of another element to the existing list, but that element in itself will be a list, aka the thing that you passed in. So be wary of what you're using and make sure to have your cheat sheet that they or not the cheat sheet but the study guide that they provide you, and that'll give you a pretty good idea of when to use what.
Yeah, okay, so we can just go over this question. I've written the number on top if anybody wants to pull it up too. This is fall 2017 midterm 2, question 4 part A, and the question is given two sorted linked lists, and over here the entire skeleton, it's basically dependent on the fact that both lists are sorted. So that's something that you really need to keep in mind, which is why this structure looks really unintuitive at first, especially this part. But yeah, if you keep in mind that both linked lists A and B are sorted, then this is actually really helpful. Yes, since the skeleton is kind of weird, we can just start with the easiest one. So let's look at the first blank. So return false over here. This would tell us that this is a base case. So let's just look at this over here first. In what conditions, what possible condition would there be at which you would return false? At the very ending of your entire function. That's either when so you would be returning false in the instance that you've gone through the whole of A and there's no value that matches in B, or you've gone through the whole of B and there's no value that matches in A. And you do know for a fact that for most linked list questions, we update links. And for most for most base cases, we're checking if something is empty. And over here, that would make sense because we would want to return false if we've traversed through either of the linked lists and we haven't found a matching value, right? So we can start writing like if A is empty or B is empty. So that's our base case. Yeah, this is generally how I like to approach skeletons that are a little weird. Just go off, like, read the lines surrounding them and see what you can use to help. So, you know, like from the return false, that the line before that has to be a base case. And you think about the possible conditions at which you would want to return false. Okay, so yeah, now let's go to the second one. So let's just think about, like, if you have a linked list, like 1, 3, 5, 7, I'm not gonna draw out the whole thing, and 2, 4, 6, this is the first doc test given, and you know that they're sorted. So the easiest thing that you can do is you can just like compare the beginnings of the two list, because you know that there's no point, like, if you don't need to actually go check this one and then check the whole of this list because they're sorted, right? So you can just go one by one. So say we check if, now at this point you know that, okay, so let's compare these two. 1 is less than 2, right? Which means that we would now, like, that's kind of redundant, so we just move on to 3 and 2, because you know that 1's not equal to 2, right? So now we move on to the next one, 3 and 2. And wait, let me actually pick an example which is like both. Sorry, let's do like 1, 3, 5, 7, 2, 7, 9. Yeah, okay. So 1 and 2, say you compare 1 and 2, you know that 1 is less than 2, and these are both sorted. So yeah, so we can move on from 1. Now we check 3 and 2. You know that that's okay. So now 3 is more than 2. So at this point, like, what you can do is, yeah, so this is where like their switching thing comes in. Or wait. Okay, yeah, let's go with the recursive call first. At what instance would you immediately return true? So there's like 2 possible ways, right? One is like at the very beginning, both elements are the same, or then you have to do the hard work and go through the rest of the linked list, right? So like the first condition in which you can like return if something is true is if dot first of both are equal. So you would return if a dot first is equal to b dot first. So this is one possible condition. And then either this can be true or another thing can be true. And then over here, this is most likely, like, you get the hint that this is going to be a recursive call because this doesn't seem to fit like a recursive call structure, right? So you just like use the skeleton to give hints to yourself. Then you check both. I'm going to leave this for now just because we can move on to the rest of it first. Yeah. Okay, now over here, what exactly are they doing over here? If there's some condition which is true, then they switch both links. Then they switch both the linked lists. So why would we want to do that? The only reason, like, okay, so like what this is basically kind of a hint where you want to where you want to switch both linked lists. I don't really know how to explain this, but yeah, basically you would want to switch both of them because at any one point you can only compare, like, you can compare using dot first, and then you can update one of them to go to dot rest, right? You can update one of the linked list to go to rest. So at this point, say we compare a dot first, you check this in comparison to b dot first. And if a dot first, if it's more than b dot first, then a, okay, let me get another example over here. 1, 3, 4, 7, 2, 4, 6. say we've reached at this point over here. If A dot first is more than B dot first, which it is, then A becomes B. So this is A right now, this becomes B. And then they're saying if A dot first is more than B dot first, then we switch the two, which means now B is this and A is this. And in your recursive call, you're updating one of the linked lists because you want to compare for each element over here, you want to compare it to this and you want to compare it to like the rest ahead. So since they've not been switched, we can update one of them to make it A dot rest. And then this is B. Now realize that like if this was all reversed, you could also have like A and B dot rest, but just because of their skeleton, we're gonna go with A dot rest and B. Yeah, if Arjun has any more inputs on this question, because this one's kind of confusing.
No, I mean, you seem to have explained it pretty well. So, I mean, yeah, yeah, I don't think there's anything I can add. You explained it very well.
Okay, yeah, this is kind of a confusing question, but just like see if that makes sense. Okay,
Yeah.
and now Karim will do the rest of the questions in other AI. And yeah, is Karim here?
Hello. I'm gonna go question 11 on the left. Okay.
Okay, I'm just gonna stop sharing.
Okay.
Kareem, if you need
so-
me to draw anything for you, I can do so.
Yeah. Yeah. Okay, give me a second. Okay. So we have question 11. I can, yeah, I think it's better if we just have it as you and I can just mention anything that we want to draw if necessary. But so if everybody can bring up the question on their own side, I guess that'd be nice. So we want to implement long pass, right? And so once we return a list of all paths in a tree with length at least n. Okay, so it wants us to return the list of all paths in a tree with length at least n. So we return. Okay, so do you have any like specific questions on this problem you want to be covered, Anita? Like, are you wondering like is there a specific part of the problem you're confused about, or do you want me to like just like go through it and sort of like explain what I'm thinking when I see this problem? So it's my first time seeing recursion in the for loop. Oh, okay. Okay. Let me go through the problem, and then once that like appears, then we can like talk about it. So we want to turn a list of all paths in a tree with at least n. A path in a tree is a linked list of a node just like the root and with ends at the leaf. Okay. So I have a couple of thoughts already, right? So first it wants to return, so we obviously know that it wants to return the thing of like length n, right? If we want to get to depth n, then we want to return that list. And so what I'm immediately thinking is that we probably want to save like 2 forms of data. So, or I guess technically 3 forms of data. So we probably want a helper function. I guess they did it a different way. Maybe not. But so I guess just the way that I'm thinking about it right now is that what we do is that we have our original list, right? So for example, I think on the doc test, it's 3, and then it has 3 children. Unless I'm reading this wrong, where it's like 3, 4, 4, 5. And then it wants us to find. Oh, wow. This stock test is actually kind of annoying to read. I guess let's just make our own example. So if we just have like 1, 2 as like, so 1 is the parent, 2 is a child, and then 3 is another child, and then 3's child is 4. We can do it like that. And then we just want to return a path, all path of length. Let's do 3 just to do that. So ideally the path that we should be getting is 1, 3, 4, and then not 1, 2. Okay. And so when I think about this, I think, okay, we probably want to count for depth, right? Because that's like a pretty easy way to know like how long our list is going. And let's see, does it want to return up of the 2? And it wants to return at least 10. So that means that we can have multiple paths and they can have varying length. So I guess this isn't accounted for in this specific problem, but we can get to it later. So first thing I'm thinking is that we want to return the path that's of a certain length. We can do that by looking at our depth, and having our depth is another useful value for us to have. And the easiest way for us to return our path is by saving the data. Oh, I see. So I mean, you understand the question, but this one for people, you can just go to solution and why it is that way. Okay, sure. So if you want to go directly to the solution, might be really annoying to like turn it all over. So I'll just put in the Zoom chat to be able to look at. This is poorly formatted, unfortunately, but anyways, so we know we need our paths, right? So we just have our paths as a list, right? Because that is the easiest way for us to save information. Because we can't just be returning the tree, the whole tree itself, because that gives us too much data. It doesn't give us a specific paths. And we can't be returning the specific node because that's too little data. So we know that so we set up a list and we know that we want to be continuously adding in our values, adding in our tree nodes. So we can save this and we can make our proper tree. And then we know if n is less than or equal to 0 and tree is leaf, they want to append it. Okay, so this is saying, so it starts off basically with like the value. So say our depth is 3 in this example. If our depth is 3, then the reason why the solution on its own is, the reason why the solution on its own has n less than or equal to 0 is that we know that we can be checking our depth by just changing the value of n itself. Because if we start at 3, then we go down to our next child and we can decrement n. So n becomes 2 for the first child, and then we decrement it again, and then n can become 1 for the third child, or the second child, sorry. And then we check if it is a leaf. Okay, so we know that if it is a leaf, that it can have no more paths. So we don't need to worry about continuing any further. And then so that's why we can simply just append the tree itself, the link of the tree itself. And then, so that's like one check we do. And then there is a case where it isn't a leaf. And that case has a bunch of branches. And then at that point, we know that what we need to do is that we need to be checking. So for path in long path b minus n. So long path in b minus n, or bn minus 1, sorry. What that is basically doing is that we take our recursive leap of faith or whatever, and that's basically telling us to return the longest paths, everything below our current node, right? That's basically what it's saying. So this is actually really helpful to think about because it allows you to make your problem a lot simpler. So instead of having to worry about going from 1, 3, 4, we can just go at 1, and then we can say, okay, just solve this problem for 3, 4, or solve this problem for 2, and then give me the result. And then if the result is what I want, then I can just stick 1 on at the top. So that is the purpose of the 4 path in long path bn minus 1. And that's why we're able to append tree.label and path to it. We're just basically just sticking on the head because we've already, through our recursion, we've already solved for the easier examples where it's, for example, for it's 2 or for if it's 3, 4. Let me know if that makes sense or not. So what do we get from this again? Okay, yeah, so that's a good question. So if we look at our example, we have 1, 2, and then 3, 4. If we do long path b n minus 1, we're assume that this is like the first time we're ever running this code, right? So we're at node 1. What that's basically saying is that for the branches of node 1, return the value of the long path of that value minus 1. So if our long path right now is 2, or let's say, yeah, we can just say 2. So what that basically is saying is that once we call, we're basically calling long path tree 2, and then that would be like 1, because n minus 1, 2 minus 1, right? And then it'd be the same thing for 3. It'd be doing the same thing. And so the result of this is that it is making it such that it gives us the correct values of its children. So I guess the simplest way to think about is essentially breaking the problem into much smaller values that are easier to run, or it's easy to compute. So and we just look specifically at the example again. We know that 2 isn't right. 2 doesn't fit the value that we want, but 3 does. And so it's hard to like conceptualize that when you're starting at node 1, but you can just go down a level and then you can compare it to your new decremented value, and then that will give you the value that you want. Let me know if that makes sense. I think, if you give me a second, I might be able to word this better. Basically, okay, yeah. So I think I might have an explanation that might make this slightly easier to understand. It's a recursive call that is just giving us the children of the current node who fulfills the requirements that we're looking for. And in this case, the requirements that we're looking for is that they're of a certain length or longer. Okay, and so that's why we have n minus 1, because our original node is looking for lengths of n, right? But because we're going down a level, we want to compare it n minus 1. And then so that's the result.
So one way of thinking about this is, once you've gotten several options, if you look at the spec for the question, which I will go back to just for clarity's sake, is if you have something of this form, notice how the options include both, here. Yeah, we have both 0, 1, 2, 0, 1, 3, 4, 0, 1, 3, 4, and so on. And the thing is, we're able to take multiple paths, but it says specifically that it needs to be at least n. If we have a value or a path, a valid path that exceeds length n, we are actually going to be decrementing to the point where we go to the negatives. That is the reason we have n minus 0 as our condition that we're checking for. And the leaf is basically just to make sure we're at the end, in which case we would just return what the label there is. If it's not a leaf, then there's a different action that we're going to do, being we save whatever our current path is, and then also add the paths that are below that. AKA, we can have a 1, 3, 4, and let's say we had like a 5 here or something. We could have 1, 3, 4 as one valid path and 1, 3, 4, 5 as also a valid path. If that was to make sense, that is. But yeah.
The appending is saving the path. So when we do, so 1, 3, 4 solves our condition already, right? It's already the length that we want. So like, okay, this is what we want. Let's just append it immediately. So we're appending the value into paths. So that's saving it. And then we're checking again by going into this for loop and then checking the children of 4 and seeing if it also has more values that fulfill the path. But I think specifically for this code though, Arjun, it is not really doing that. I think, unless I'm mistaken, I think the way this code is supposed to run is that it doesn't save multiple. I think it's only saving the longest most path, which is why it's checking for is leaf.
Oh, I see. Because
Yeah.
the thing is, I thought I did this problem earlier today, which is why I
Oh,
bring
maybe.
this up.
I've definitely seen a problem that is of that. So where do we get rid of the path
Yeah.
that doesn't satisfy the condition of number n? So, oh, I see what you're saying. Okay. So, the way that this works is that actually, so it's only ever saving paths that work, right? Paths that don't work are never actually put into path, if that makes sense, right? Because there are only two times where we ever are appending to path, right? The first one is if it meets the original if statement, right? If it meets that condition, then we add it in. But it meeting that condition already means that it's correct, that it's already fulfilling the requirement that we want. And then the other condition is that if its children meet the condition that we have set for it, and then the fact that its children are able to meet that condition means that the whole thing in general fits that condition. So that's why we're adding it in into the from the path. That's where the path is being appended in that for loop. So for path in long path bn minus 1, you will only the value of long path bn minus 1 will only ever be paths that meet the condition. It will never it's a list that will only ever contain that, right? Because remember that the return value of long paths is paths, which is a list, right? So the value of that list will only ever be valid paths. Does that make sense? That's where like that recursive leap of faith is coming in.
Essentially, think about it this way. If I was to tell you that you need at least 5 buckets to carry all the paint, at least 5 also includes 6, 7, 8, and so forth. As long as you meet the initial condition of having those 5 buckets, having more than that is also a valid kind of satisfaction to that condition, given it's greater than what you wanted it to be.
Okay. So homework 5, question 4. Okay. So have path. So I'm confused on how to iterate through the tree and the given word. Okay, so write a function takes a tree in a string term and returns true if there's the path that starts from the root where the entries along the path are spelled out term and false otherwise. Okay. So I'm confused on how to iterate through the tree and the given word. Basically, I see that label is not equal to turn into control. Oh, okay. So if we look at this, right, if we're given, like, for example, the word like hello. Yeah, so we're given this tree and we want to see if it can fulfill the word hello, right? We know that for us to compare two words to each other, right, they must have the same letters in the same positions, right? That's the only scenario where the words are the same. And so because we have a tree structure, we can't compare the whole tree at once. We can only compare nodes at a time, right? So we start off at the simplest, or at the only case that we can access right now, given our tree, and that is the parent node. So we're at our parent node and we're like, okay, does this first letter match the first letter of the word? That's what we need. That's the immediate check. And if it does, then we're like, okay, there's a chance that this works. It's not guaranteed, but it's possible. So now we go down to its children, right? Because we know that the next word or the next letter needs to be there. Like the tree needs to have a child, and then that child must have the correct letter. So we go to I, and then we're like, wait a second, I does not match E. So that's immediately we end the program right there. We're like, okay, well that didn't work. So we check our other child, which is E. So E matches, and then we're like, okay, let's keep on going. So then we have to decide between. So then we visit L and Y. Y doesn't work, but L does. And then I guess for this problem, you don't have to worry about it because you get to the end of the letter. You go L, then L, then O, and you're like, okay, well, the word has no more elements, right? And neither does the tree. You don't actually need to worry, I believe, about the tree having an extra element. Yeah, like for example, I think if O has a child, that doesn't really matter. This would still be correct. Yeah. So I don't think you need to worry about that. So basically, the only condition you really need to worry about is that if the word itself still has more letters left, but your tree doesn't, then that's immediately an error. We know there's a problem there. Or if the letter at the index of the tree doesn't match the letter at the index of the word. Let me know if that makes sense or not. Okay, cool. Does anybody have any other questions or no? Oh yeah, fall 2019, what would Python do? Okay, and this is for OOP. Okay, so we can just start at the beginning. I think I remember. I think I remember messing up on this actually when I was studying for my exam.
Her question was before
Oh yeah.
oh yeah, she basically before she also wanted to check if there's any method or tip to keep track of the variables and stuff in object-oriented programming. And I would use box diagrams, but yeah, it's just there's anything. Yeah, basically I think that's the main question.
Yeah, I mean also I think they even give you an overview of how you can do box diagrams in the videos. Like there are TA videos walking through the videos that I recommend. That's what I used to study a lot for these exams. Yeah. So oh yeah. I think Arjun can maybe show it. It's it's next to it goes solutions tagged and it has a video, and then that video is that is a playlist of the TAs going through the problems. I think it's definitely a very good resource. I recommend you guys use. But yeah, so if you saw me to go through the problem, This would be for, I'm confused on the P35, or sorry, the pi 3.5. Okay. So we're wondering, okay, so we got to follow through like the life of pi. So pi starts off as a dictionary. This is interesting. This is so it's a dictionary whose value is another dictionary whose value is a letter. So pi 356. And so we're wondering, why does pi change? Okay. I'm actually wondering as well. Let me look through this. 5, it has the list 7, thon 7, 3, 4. Why does pi 3.5? So I'm pretty sure. Unless I'm mistaken, is it asking for the length? So I think what's happening here is that, so you have pi 3, right? So that's saying the value of that dictionary with value 3. So that's our next dictionary, right? The dictionary of 5, and then the list with the value 7 in it. And then what it's then saying, so oh wow, okay, wait, this is actually tricky. Okay. I think I see it now. Okay, so we know that pi originally is a dictionary with the value 3, or the key 3, whose value is another dictionary, right? And that dictionary has the key 5, and that key's value is the list 7, right? But then there's thon. Thon is a dictionary whose key is whose key is 5, and then whose value is 6. And then it has a next element whose key is 7 and value is the dictionary pi that we have before. So what thon 7.3 is doing is it's saying thon, which has the key 7, so that's immediately giving you pi, right? Because that's the value of the key 7 for the dictionary thon. And then it's checking the key of that. So it's checking for pi's key associated with 3. And then so that is our other dictionary whose key is 5 and whose element is 7, right? And it's setting that value to the original thon dictionary. Like the whole thing is being replaced with that value. So instead of pi being the key 3 and then the value of this dictionary 5, 7, it actually becomes 3, whose value is thon itself. So it's the 5, 6, and it's the 7 pi. And then so the reason why the actual answer is 6 here is that we check, so first we put in pi 3, right? So pi 3 gives us thon, okay? It gives us that whole dictionary. Then we're, okay, what key is associated with the value in thon? And then you see here that the 5 key is associated with the value 6. And so that's why 6 is being returned. Let me know if that makes sense or not. Yeah, that's actually tricky. God, 6-1A really is something.
If you do want more help with the WWPD questions, I would really recommend like the TA walkthrough videos, like you said.
Yeah, I think
Like they go over the whole thing and they're like 45 minutes long.
Yeah.
Because they're really comprehensive. So just check those out.
By the way, we are nearing 9 o'clock, meaning the review session is about to end. So we'll probably answer maybe one more question if there's any. But yeah. Any last second questions, guys? Okay. Looks like nobody else has any questions. So we will wrap up this unofficial. Oh, never
Our
mind.
map, filter, zip, reverse, tuple stuff we can use without being asked to. Yeah, I'm
Yeah.
definitely sure you can. Yeah.
In fact, I think they did expect us to do it like last semester.
Yeah, last semester, map, filter, zip all appeared on the exam for midterm. For midterm two specifically, actually. Yeah. So definitely be prepared for that. Definitely, yeah.
Yeah, I'd actually
they're just
recommend like
generally
being
useful.
really thorough with map, filter, and zip.
Yeah. What was it? It was like a standalone question, I think.
Yeah,
Yeah,
that
there
was
it
like one of
is.
the function questions they wanted us to use zip. Yeah, there.
Oh.
Yeah,
Yeah,
so
they
they-
love using maps and filters.
I think they do give you a hint though, or at least for our exam, they were nice enough. Yeah. So what zip does is that it takes in two arguments, right? And these are two iterables, and it combines them into a list of tuples. So, for example, say you have like the tuple 1, 2, 3, and then the tuple 4, 5, 6. When you do zip on that, it will give you 1, 4, and then 2, 5, and then 3, 6. And then this will all be in I think it's in a massive, I don't remember if the result is a tuple or a list, what the output is, but you can like access the values like that. Yeah, no problem.
All right. Any other questions? If not, we will wrap up now. Feel free to send any questions to me on Discord. I will be there to answer. But other than that, thank you all for coming. And thank you to the other AIs for being so kind as to help me with this. It was a great experience working with them. But yeah, good luck, guys. Don't
Best of
stress out
luck.
too much with your exam. You're all gonna do great. Just keep calm, study a bit more. You know, you all do great. But yeah,
Yeah.
have a good
Best of luck.
evening. Bye. Bye.